There are 5 types of fog that have been identified. These are radiation fog, hill fog, advection fog, frontal fog, and Arctic or steam fog. Let's look at these in turn. Radiation fog is caused by the loss of heat from the Earth's surface at night. The air at low levels is called by conduction, and if enough cooling takes place, the air will reach its dew point temperature, become saturated, and allow fog to form. The conditions that are necessary for radiation fog are a clear sky, high relative humidity, and light winds of around 2 to 8 knots. This allows some mixing of the layers of air and will continue bringing moisture down from higher levels. If the wind is calm, dew is deposited and no fog forms. Radiation fog forms overland at night and through the early morning period. Through the autumn and winter months, likely conditions include low-lying areas, such as broad valleys, especially where there is a moisture source, such as marshy ground or a river, and anticyclones or coal areas, which give light wind situations, and so lead to the formation of radiation fog. Radiation fog will often be a few hundred feet, 100 meters or so thick, and can, on occasion, be 1,000 or more feet, 300 to 400 meters deep. Insulation will generally lead to the thinning and eventual dispersal of radiation fog as the sun warms the ground and the air in contact with it. Convection and stirring of the lower layers of air will take place. This will lift and eventually clear the fog. An area of radiation fog will be cleared mainly from below, but also from the fog top and around the edges. In the UK, radiation fog typically clears by these means by around 11 o'clock in the morning. The actual clearance time will depend on the depth of the fog and the sun's strength. Increasing wind will cause mixing of the atmosphere, helping usually to lift fog into low strut as cloud. 2 further mechanisms that will clear fog very effectively are increasing cloud at higher levels, which inhibits the loss of radiation, and the advection of dry air into a foggy area. Hill fog forms when a low cloud covers an area of high ground, such as a hill, mountain or plateau. It can be localized or very extensive indeed, and is a major hazard to low-flying aircraft. Visibility in this type of fog will usually be less than 200 meters. Advection fog is formed when warm and moist air moves across a cold surface. This surface can be either land or sea, but sufficient cooling of the air by the underlying surface will result in the formation of advection fog. This type of fog is often quite extensive and up to 100 or so feet in depth. Shallow coastal waters in spring and early summer, or where upwellings of colder water occur, are areas often prone to advection fog. Such areas include the ground banks of Newfoundland, the North Sea, and the Kamchatka Peninsula in the northern Pacific. Conditions necessary for the formation of advection fog are Sufficient wind speed to move the air. Around 15 knots is typical. A high relative humidity. And a cold underlying surface, with a temperature below the dew point of the overriding air. This calls the lowest layers of the air causing saturation. Dispersal of advection fog is usually by drier air moving into the area, or by an increase in wind speed, which lifts the fog into low cloud. Frontal fog occasionally forms just ahead of some warm and occluded frontal systems. It is caused by the precipitation dragging the warm moisture into the cooler air below the front. This moisture in the air then condenses into water droplets, which can be seen as fog. The belt of frontal fog can extend as much as 200 miles ahead of the front itself. Clearance will usually follow the passage of the front at the surface. Steam or Arctic fog is quite rare, but occurs over the sea in polar regions. For example, in the fields of Greenland and northern Scandinavia. It forms when cold air blows offshore over a warmer moist surface. The small amount of evaporation from the sea surface causes saturation and the formation of the fog, which looks like plumes or ribbons of smoke rising from the sea. If stable conditions exist, the fog will deepen by as much as 500 feet, 170 meters. The fog can be very persistent, but will usually clear when air with different characteristics moves in, or when an increase in wind speed occurs. Let's now consider how the visibility can impact on the Aviator. RVR, runway visual range, is only reported when either the horizontal MET visibility or the RVR is less than 1500 meters. The visibility on approach can vary significantly from the horizontal METVIS. There is no direct connection. Note, however, that RVR is reported for the touchdown zone only and can be determined by placing an observer 76 meters from the center line of the runway and counting the number of marker boards or lights in the appropriate direction. In the UK, standard RVR reporting increments are 25 meters between 0 and 200 meters, 50 meters between 200 and 800 meters, and 100 meters above 800 meters. Reports are taken every 15 or 30 minutes, depending on the amount of air traffic. We mentioned earlier how the visibility can be measured using a transmissometer. We can use a system in which 3 transmissometers are placed alongside the runway to obtain an IRVR or instrumented runway visual range. Readings are then given to air traffic control, one for the touchdown point, one for the midpoint, and finally one for the stop end, and reported in that order. For example, R27L, 600, 400, 550 means, on runway 27 left, the touchdown visibility is 600 meters. The midpoint visibility is 400 meters, and finally the stop end visibility is 550 meters, as measured by the transmissometers. If only 2 readings are given, the first relates to touchdown, and the second is prefixed as follows. 600, stop end 550 means, the touchdown visibility is 600 meters, with a stop end visibility of 550 meters. Similarly, 600 midpoint 400 again means the touchdown visibility is 600 meters. But this time the midpoint visibility is 400 meters. Midpoint or stop end values are emitted in two instances. The first is when the midpoint or stop end values are equal to or higher than the touchdown value and have a value greater than 400 meters. For example, readings of 300, 450 and 600 would be reported as R300. The second instance is when the midpoint or stop end values are equal to or greater than 800 meters. For example, 1850 and 900 would be reported as R1000. There are some other details we must know. RVR values less than 50 meters are reported as RBL0050 or M0050. RVRs greater than 1500 meters are reported as P1500. There may be a 10-minute trend reported. U means the visibility has increased over the last 10 minutes. D means it has decreased, and the letter N is used if there is no change. The letter B should be included if there are great variations in the measured visibility. When operating above or within fog or haze layers, there are some points worth noting. Oblique visibility is the distance you can see along the ground when operating at a specific height. If you are flying in a haze layer, you will have a greater oblique visibility if you were to descend within the haze layer. Conversely, if operating above the top of the haze layer, you could increase the oblique visibility by climbing well above the haze layer. If there is a shallow fog layer covering an aerodrome, the pilot flying an aircraft overhead might think that the visibility is quite reasonable. However, lower down on final approach, conditions will appear much worse as the pilot has now got to view through a greater depth of horizontal fog. That completes the lesson on visibility.